We have a review type problem, something that we should be able to answer using the tools we already know. So we have not one integral, but double the fun. Two integrals. Integral from 0 to 1, integral from 0 to 1. Ah, rectangle. Cosine e to the y dy dx. Integral 1 to e, integral log x to 1, cosine e to the y dy dx. Now this one's not a rectangle because you see there's a function in there. When you see functions in the bounds, it means not rectangle. It's another shape. I don't know exactly what shape, but it is what it is. Probably we'll have to figure it out if we want the answer. You've had a few moments. Do you have an answer? Would it help if I knocked out a possibility? It's not A. Okay, any answers yet? D. D is the right answer. Nice. Nice. All right. Good. Good. So let's talk about this. Now, you look at this integral and say, I don't want to integrate this with respect to y. Well, why don't you want to integrate cosine e to the y with respect to y? Well, because you can't. Right? There's no way to integrate, there's no antiderivative of cosine e to the y. It's just not going to happen. Okay, so you don't want to integrate with respect to y. And I say, okay, I can integrate with respect to x. And if you do it, in this first round, okay, sure, you can integrate with respect to x, but how do you get the next layer? So there's problems here. But at this point, you probably say, well, wait a second. These two integrals seem related. We're integrating the same function. What's different about these integrals? Bounds. So let's talk about the bounds. So let's start with the first set of bounds. We have 0 to 1, 0 to 1. Now, if we translate these bounds, because one of the things we want to learn to do is read off the bounds. What are the bounds telling us? The outer layer tells us what? X bounds, and x does what? 0 to 1. The inner layer tells us what? Y bounds, and y is doing what? 0 to 1. So, at this point we say, we're going 0, 1, 0, 1. It's a rectangle. Even better, it's a square. Hip to be square. Bum, bum, ba-da-da-da. Okay, there we go. That's the first integral. Now we'll do the same thing, but with the second integral. Okay, same process. We want to understand, what are the bounds telling us? What do the outer bounds tell us? X goes from 1 to e. What do the inner bounds tell us? Y goes from ln of x to 1. The bounds are descriptions of regions. Now, e, that's about 2.7, say roughly here. Log of x. Now, I don't know much about log x, but I know it goes uphill. What is log of 1? 0. So it's going to pass through this point. That's very convenient. Does anybody know what log of e is? Oh, it's 1. Also very convenient. So the log function is doing that. So this is our y equals log x. So from 1 to e, we're going from log x up to y. That means we're doing this. All right, so that's our current setup. And as we look at this current setup, we've essentially said we're slicing in this fashion, up and down. And that's one of the reasons why we have to split the integral at 1. Because before 1, when we slice, the bottom is bounded by the axis. But after 1, it's bounded by a different curve. We changed the behavior, so we have to split the integral. Now, what's our hope? Our hope is, what if we split the other way? Not dy dx, but dx dy. So that's the goal. Can that get us out of our quagmire? So let's think about how we can describe it. We're going to set up our integral. It's the same function. We're changing dx dy. So we got to think about the y bounds. Where does y go between? Which y values do we hit? 0 to 1. So that's our outer layer. Now, given an y value, where does x go from? From 0 up to what? Well, up to this curve, y equals log x. But what's another way to say y equals log x in terms of x equals something? X equals e to the y. So we change our bounds. So a different description, instead of having 2 pieces, we can do it as 1 piece. All right, so we have our 1 piece somewhere in the blue, the deep blue. All right, let's try to integrate this. What's the integral of cosine e to the y with respect to x? Well, notice, what is cosine e to the y with respect to x? It's a constant. So the integral becomes cosine e to the y x, evaluated from x equals 0 to x equals e to the y, because these are our x bounds, right? X equals 0, x equals e to the y. Now we have to evaluate. The good news is when you plug in 0, you get 0. When you plug in e to the y, you get e to the y. So you have cosine e to the y times e to the y dy. How do we evaluate this? Channel your inner Calc 1 student. It's inside of you. It's that pure, innocent soul. What do? Use substitution. So you'll let u equal e to the y. Then du is the derivative, e to the y dy. And then you're like, nice! Because we get an integral, cosine of u, du. And let's talk about our bounds. What happens when you plug in y equals 0? What is u? 1. E to the 0 is 1. What happens when you plug in 1? E to the 1 is e. Integral of cosine? Sine. From 1 to e, positive sign. That's why you'll notice here we had 2 options, different sign choices. So sine of e minus sine of 1, which in fact we see there is option D. All right. Any questions? Okay. Do you want to do any more practice with setting up bounds, or should we jump to today? More practice or today? Today? What a shame, more practice. Well, we'll save you for the end. Who knows? Who knows? All right, so thought for our day. Some people have no idea what they're doing, and a lot of them are really good at it. And this is from George Carlin. And he was I think humorist is probably more accurate than saying comedian. And I like this thought because I think it captures what sometimes happens to students. A lot of students have sort of a vague idea of what they're doing, and then they do a lot of work that's in the wrong direction. And they spend a lot of time not being very effective. I strongly encourage you, learn what to do. Yes, there's a lot to learn. I understand that. But you need to become someone who has an idea of what they're doing. Because you need to know what you're doing. You can't just randomly fill a page and hope for partial credit. Because 2 or 3 points out of 10 on a problem, sure, if you do that for 1 or 2 problems, that's okay. But if you do that for all the problems, that's dangerous. So be careful. Now, what's our goal for today? We're going to talk about integration using polar coordinates. You might say, isn't that what we did in Calc 2? Well, in Calc 2, you did do integration with polar coordinates, but you were after a very specific thing, which is you were after just area and nothing else. We're going to do something a little bit more general. Now, the other thing is we're going to practice rewriting integrals to take advantage of polar coordinates. And by that, I say maybe we're given an integral in terms of x and y, which is not very happy. We don't want to integrate it. But we take advantage of saying, the problem is we're looking at it in the wrong coordinate system. We can reformulate the problem, instead of in Cartesian, into the polar coordinates, and that can make the problem accessible, and we can succeed. So in terms of our formula sheet, we're adding just a touch today. We're adding that we can change from the dy dx, which is our piece of area, to r dr d theta. We'll talk about where this r is coming from. Just as a reminder, we do have some information about polar coordinates on the formula sheet for reference. All right. So let's get into it. And first we'll start with some philosophy. For reference, this is just a quick reminder, how do Cartesian coordinates work? You pick a point and you say I can describe it by 2 numbers which represent distances that I've moved. So I have a distance moved in the direction I call x, a distance moved in the direction I call y, and those 2 numbers give me a location. In polar, it's slightly different. I do still have 2 numbers, but one of them is a distance, the other one is a direction. So it's like I'm pivoting at the origin until I'm facing the right way. Once I'm facing the right way, I move forward r to get to my correct point. Now you can lay them on top of each other, and that's where we get the formulas for x equals r cosine theta, y equals r sine theta, x squared plus y squared equals r squared. And there's this note. Pick the coordinate system that makes the problem simple. Notice that when we change our coordinate system, we don't change our space. We're not trying to change our problem. Ultimately, what we're trying to do is change the description of what things are in the space. And in different coordinate systems, sometimes descriptions can be simpler or more complex. So our goal is to say which description is easier to work with. Now we're going to talk about the following. We're going to probably say this 4 or 5 times in the next 2 weeks. So it's probably really important. Whenever we think about doing an integral, there's always 3 important parts of an integral, the 3 aspects of any integral. So the first thing is we have to describe our region. So this gets back into choose the coordinate system that makes the description simple. So that can depend on our coordinate system. We have to express the function. So if we are in the Cartesian coordinates, we express things in terms of x and y. If we're in polar, we express things in terms of r and theta. And the third thing, which is easy to forget about but super important, is we have to think about how we break things into small parts. Because integration is about breaking things into small parts and adding them up together. Now, we're so used to starting with Cartesian because it's a very simple system. Another name for Cartesian is rectangular. We like rectangles. They're super easy for the mind to understand because they're nice and flat. Now, when we talk about breaking things up, the way you should think about it is I say, I'm going to perturb my variables. So if I'm thinking of x and y, I think about a little bit of change in x and a little bit of change in y. And I say, okay, what do you get as your shape? You get a rectangle out. And so from here, you say, aha, the bit of area that you're getting is dx dy or dy dx. So this is your Cartesian. But now we think about polar. We say, okay, we're going to perturb r and we're going to perturb theta. But notice perturbing theta is perturbing the angle that we're coming out of. So we're just sort of changing how we're sweeping here. And the r changes what's happening over there. So now the thing is, what shape do we have? Well, it's not a rectangle anymore. What is it? One way you can think about it is if you were to just let theta go all the way around, it's like you have the very edge of a circle. In terms of pizza terminology, it's the crust. So this is like a small part of the crust of the pizza or pie, whatever your favorite circular thing to eat might be. Cookies, so many options. Now the question, what's the area? Well, I have a start of the derivation. Up here, there's a nice geometrical fact which says, suppose you have a circle of radius r and you cut out a wedge of radius alpha. Well, if you take the area of the wedge divided by the total area of the circle, that's equal to the ratio of the angle in the center alpha divided by the whole revolution, 2 pi. Or the area of the wedge is 1/2 times alpha times r squared. And this is where alpha is measured in polar. So, sorry, polar. I just said polar. I should have said radians. So now, how do we get this? Well, the idea is if I want to know this portion of the wedge, well, what we can do is we can just sort of fill it in. We'll say we'll find the total part of the wedge, which this involves r plus a little bit, I'll call it delta r. And then we subtract off this portion, r. So if we carry out that computation, well, what do we get? The area is approximately 1/2. And I should say that our angle here, we're going to keep it as d theta. So 1/2 d theta, r plus delta r. Should put the consistent squared minus 1/2 d theta r squared. So big piece minus little piece. And if you go a little bit further in here, because who doesn't like doing algebra? Algebra, our old reliable friend. We'll get the following expression. So 1/2 d theta r squared plus d theta r delta r plus 1/2 d theta delta r squared minus 1/2 d theta r squared. And now we just say, aha, Those cancel. Beautiful. And this we can ignore. Now you might say, why? Well, because of the nature, it's so small in comparison to this term. Notice this basically has two small pieces. This has 3. So in comparison, this dominates. So this is going to r dr d theta. So that's the r here. There's your dr. There's your d theta. So that's where it's coming from. Now, you might say, okay, that's a very convincing pizza story, but is there another way to see it intuitively, that you need r? Well, imagine I look at this piece down here. This also has length dr. Look at these 2 areas. Are they comparable? No, one's much smaller. So as you go out, your size increases. So you should say, my area should depend on r. So that's one good way to think there should be an r. Now let me give you a second good way. When you're talking about area, how many distances should be involved? 2. Look here. X is a measurement of a distance. Y is a measurement of distance. So 2 distances make up an area when you multiply. R is a measurement of distance. But what about theta? Is theta a measurement of distance? No. If we didn't have the r, we'd be missing our second measurement of distance. So you need that something there to be a measurement of distance. So that's the second reason why we need something like r to be there. All right. So with that, we can work through some problems. Any questions before we get going?
Are there any cases where we need to set to ignore?
Are there any cases where we need to do what?
Use the thing you said to ignore.
No, there will never be any cases where we choose to ignore. There's sort of this idea of infinitesimal calculus or things like that. This is a little bit of the hand wavy, you're in a part of mathematics known as analysis. And in the art of analysis, the big question is, what's important? What can you ignore? And so when we say ignore, what's small in comparison to everything else? And it takes a while to get good at it. I don't claim to be good at it, but I claim to be able to get a passing grade. And I'll pass on what I know. All right. So, here's the problem. Find the integral 0 to pi, integral 0 to theta, pi minus r, r dr d theta. So, you might look at this and say, this kind of feels like doing the same thing that we were doing before. Namely, we want to integrate, and we have 2 layers. So we should just integrate with respect to each layer, and won't that give us the answer? And the response? Yes, it is. Just because you change symbols from x's and y's to r's and thetas doesn't change the basic ideas. You're still integrating. So we can just carry out the integral and just remember what we need to do. So we say, all right, let's start with the inner layer. Now, in the inner layer, what are we integrating with respect to? R. So how do we treat theta? Constant. It doesn't matter, there is no theta, but if there were, we would treat it like a constant. Now, before we integrate, is there anything we should do? Yeah, we should distribute. All right, so this becomes integral 0 to pi. Then we're working on the inner layer, so we're cleaning it up. We say we are nice to ourselves, so we're setting ourselves up for success. We'll distribute the r through before we carry out the integral. What's the integral of pi r minus r squared with respect to r? It is tricky. Or is it? If I said integral of pi x minus x squared with respect to x, would you still be pausing so much?
Pi over 2 r squared minus r cubed over 3.
Okay, pi over 2 r squared minus 1/3 r cubed. Okay, all right. And we're evaluating. And I like to say I'm evaluating r. So r equals 0, r equals theta. When you plug in r equals 0, what comes out? 0. Good. So we just really need to plug in theta. So 0 to pi over 2 theta squared minus 1/3 theta cubed, d theta. All right. Now what do we do? Well, we integrate with respect to theta. What is the integral of pi over 2 theta squared minus 1/3 theta cubed with respect to theta? Pi over 6 theta cubed and 1/12 theta to the 4th. Evaluate theta equals 0 to pi. If you plug in 0, you get 0. If you plug in pi, you'll get pi over 6 pi cubed minus 1/12 pi to the 4th. Well, they both have pi to the 4th. What's 1/6 minus 1/12? 1/12. So 1/12 pi to the 4th. Now that's the answer. So in terms of actually carrying out the integrals, it's the same thing with x's and y's. One layer at a time, treat the other like a constant, no surprises. Now, in terms of what we're actually doing, we can think about what the computation here is. The r d theta, this part on the end, what does that represent in terms of our integral? Because remember, every integral has 3 parts. R d theta, what am I representing? The little part of area. So this is the dA, cutting things up. So this pi minus r, what is that? That is the function we are integrating. So in terms of like what's being integrated, we're integrating pi minus r over the region. Now, finally, let's talk about the region. So the region we get from the bounds, and you have to be careful how to read the bounds. So what do the outer bounds tell us? It goes from theta. Theta goes 0 to pi. What do our inner bounds tell us?
R goes from 0 to theta.
R goes 0 to theta. Now, in terms of the plane, theta going from 0 to pi, theta equals 0 is the positive x-axis. You spin, theta equals pi is the negative x-axis. So we're in the top half. R equals 0, where is that? It's the origin. So we're going on the top half, we're going from the origin out to a curve. Which curve? R equals theta. Now, that curve is probably not quite as familiar, but what it looks like is that as you let theta grow, R grows. So this is the curve R equals theta. So that as you move along this curve, you're going from 0 out to R equals theta. So this is the region that you're integrating over. On a side note, this is called the Archimedes spiral, named after Archimedes, who he was one of the most famous mathematicians, and he loved math right to the very end. The story goes that he was in a city that was being invaded, and they were said, look, take Archimedes alive, we need him. And they found him on the beach, drawing in the sand. And he said, get out of the way, you're blocking my circles. And they killed him. But he was doing math right to the very end. All right, a good life, a good life. All right, we have some time. Let's see. Do we have time for 2 questions? I think we have time for 2 questions. This is an old quiz problem. I really like this one. Find the volume for the region given by x squared less than or equal to z less than or equal to 9 minus y squared. Now, you might say, wait a second. There's no r's and thetas in here, Steve. Uh-oh, you messed up. Well, it happens to me all the time. If you talk about z equals x squared, what does that look like? Z equals x squared. I see people drawing with their fingers. They're drawing parabolas. That's right. So z equals x squared, you can just think of in the xz plane, it's a parabola. And then you're just copying that parabola back and forth. All right, so there's this. It's like you took a sheet of paper and you made a trough. So you have your z equals x squared parabola. What about z equals 9 minus y squared? What would that look like? Nine minus y squared would look like a parabola, just turned upside down. And you just copy it back and forth because there's no x. So you sort of have these 2 troughs, one that's opening up, one that's opening down. You have to be above this, but below that. And you're like, what shape does that make? And I'm like, I don't know. But I don't have to know exactly. I just have to know enough to get it set up. So, how do we start figuring this out? Well, how do you find volume? What's our method to find volume? We integrate. Good. What do we integrate? We can integrate over a region in the plane something. Do you remember what we integrate? Height. If you integrate height over your area, that finds volume. So how do you find the height between these two? Subtract one from the other. So which one's on the top, and how do we know? Yeah, 9 minus y squared is on the top. How do we know that? Because it says so. I'm taking advantage. So it says, look, it's 9 minus y squared, it's the top. So you take the top, subtract the bottom. Great. Now we know what to integrate. What's our region? So how do we figure that out? What do we need to look for? Ah, circle. Okay, but how do we figure that out? I agree with you. Where does that circle come from? So they come from where the surfaces intersect. So you say, well, when does the bottom match the top? So for our region is going to be, where does x squared equal 9 minus y squared? Or x squared plus y squared equals 9. Now that's where the edges match up. We recognize that shape. That's a circle. Now which part do we want? We want the interior. Because in the interior of the circle, the top surface is on the top and the bottom surface is on the bottom. On the edge of the circle, they exactly overlap. Outside of the circle, they swap places. That's no longer being considered for our volume. Okay, so updating. We have the following. The volume we're after is the integral over the circle x squared plus y squared less than or equal to 9. That's our region. Now this, we can rewrite this as 9 minus x squared plus y squared dA. Is there anything other than the fact that we just have been talking about polar that suggests polar?
The area of the region is a circle.
Well, that this is a circle, highly suggestive of polar. That your function involves things x squared plus y squared. When you start seeing x squared plus y squared showing up in your functions, it's just trying to say polar, polar, polar. This is polar. Think polar, 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 right? So that is showing up in your region and in your function. That's like a 1-2 combination. Like this is just going to knock you out if you don't get it set up in polar. So we say, hey, idea, let's put it in polar. So we switch to polar. Now we have to handle all of our pieces. We have to think of our region. We have to think of our function. We have to think about how we're breaking things up. So maybe we'll start at the back. What will dA become? R dr d theta. 9 minus, parenthesis, x squared plus y squared. What will that become? 9 minus r squared. Let's talk about our bounds. Our region is a circle. Our region has a circle of radius 3, so we're going 3 out in each direction. Where does theta go from? All the way around, meaning 0 to 2 pi. Full revolution is 2 pi. Where does r go from? 0 to 3. Now, it's tempting to say negative 3 to 3, but remember, in polar, everything says, how do I come out from the center? How do I relate to the center? So, as you let, starting at theta equals 0, going out from 0 to 3, and you spin around, you'll see that you cover the full circle. All right, at this point, you do some calculus. And you get the answer. I want to see if we can't make progress in one more problem. So I'll say, from here on out, straightforward integration. We know how to do this kind of thing. Here's another problem. Find the integral from 1 to 2, integral from 0 to square root of 2x minus x squared, 1 over square root of x squared plus y squared dy dx. All right. Again, everything's given to us in terms of x and y. In theory, we could integrate this with respect to x and y. Our theory won't last long because we look at it and say, no thank you. I don't want to integrate that. So we say, okay, what are our options? Well, what can we do? What can we do? We can convert it to a different coordinate system. Is there anything that's hinting polar might be nice? Yeah. This in polar becomes what? R, right? Downstairs. So the function in polar is 1 over r. The dy dx in polar becomes what? R dr d theta. Already this is feeling great because you're like, hey, check it out. Now you're like, perfect. What's left to do? That's right, the bounds. There was going to be a price to pay. All right, We'll pay that price. Let's talk about our bounds. What can we say about our current bounds? What's true? X goes 1 to 2. And 0 goes 0 less than equal to y less than equal to the square root of 2x minus x squared. Well, 1 to 2, that's not so hard. Y equals 0, that's also not so hard. I'll mark it here. This is y equals 0. Now, y equals the square root of 2x minus x squared. That doesn't look so friendly. What can we do to make it look friendlier? Square both sides. Y squared equals 2x minus x squared. Or x squared minus 2x and a suspicious gap plus y squared equals 0. What can we do with our suspicious gap? Complete the square. You add 1 to both sides. You get x minus 1 squared plus y squared equals 1. Which says, oh, this is a circle of radius 1 centered at 1, 0. Now, our region is this piece. That's our region. We're going to jump back and say, this is also x squared plus y squared equals 2x. What's another way to say x squared plus y squared in a very polarish kind of way? A polarizing, perhaps, expression? R squared. And x? R cosine theta. Oh, well, isn't that convenient? Yes, it is. This curve right here is r equals 2 cosine theta. Oh, we're in the home stretch now. We're feeling the love. Okay, so let's talk theta. Our region starts off in this direction. What angle is that? 0. It ends in this direction when we pass this very top corner, which, by the way, is at the point 1, 1. Which direction is that? Pi over 4. Now, as I come, I need to go between two curves. What's my outer curve? 2 cosine theta. Oh, this is great. I'm loving it. We're 1 entry away. Just 1. 1 more and we'd have it. What's this curve?
1.
No. What is that curve? Well, it is 1, but it's x equals 1. What's wrong with that? It's x. What do we need? R. Right? These are R bounds. We need R equals something. But what's another name for x? Spoiler alert, we did it over here. X is r cosine theta. So r is what? 1 over cosine, also called secant. That's our lower bound. Now, can we integrate this? What's the integral with respect to r? Yeah, because look, there's nothing left. It's the integral of 1. So r from secant theta to 2 cosine theta d theta. Well, that becomes integral 0 to pi over 4, 2 cosine theta minus secant theta d theta. Can we integrate that? Integral of cosine? Sine. Integral of secant? Look in the back of the formula sheet. Log secant plus tangent. Ah, good times. Log secant plus tangent. A plug in from 0 to pi over 4. I know we're basically out of time. But 2 times sine of pi over 4. Do you know that? Square root of 2 over 2 times 2 gives us square root of 2. Secant of pi over 4. Anybody know that top of their head? Square root of 2. Tangent of pi over 4? Oh, come on. Tangent of pi over 4. 1. Yeah, because arctangent of 1 is pi over 4. If you plug in 0, you get 0, which means that's the answer. That is hopeless, and yet It ended up not being terrible. Switching to different coordinate systems makes the possible happen. All right, that's it for today.